Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my pleasure to welcome Brian Bailey to Microsoft Research. Brian and I have known each other for quite a while. He started doing interruptions research about the same time I did while he was working on his PhD at the University of Minnesota with Joe Constant. Now he's at the University of Illinois as an assistant professor at Champaign-Urbana. And I know that he's going to talk to us today about some of his very interesting findings in the area of interruptions. I think they're very practical findings that all of us can apply to our own product space and research. So without further ado, I'm going to let Brian take over and tell you what he's doing.
Okay, thank you, Mary. And thank you for hosting me. Thanks for coming to the talk, and thanks for watching remotely. I'm going to talk today about a topic that I personally find incredibly fascinating, and that's interruption in desktop computing. This is a topic that, as Mary said, I focused on a bit during my PhD dissertation, though actually wasn't my dissertation topic. And it's been a principal theme of my research since I moved to the University of Illinois. And what got me originally interested in this topic was this very simple observation that applications are becoming much more proactive in their interaction with the end user. And certainly that's a trend that has continued through today. And now we have this very common situation where users are engaged in primary tasks and applications that are executing in the background of their attention are periodically seeking to relay information to them. And this is typically done through notification displays or just notifications. We need to understand how to design these well, such that they have minimal intrusiveness, but at the same time, we need to design such notifications such that they do, in fact, attract the user's attention away from the primary task so that you perceive and comprehend the information that's conveyed in the notification. Even though they have, I think, a somewhat of a negative connotation to them, notifications are, in fact, quite desirable by end users and, in fact, have good utility because they allow you to acquire information updates without having to visually sample a peripheral display or application. And in fact, there's a great quote from a user who participated in a field study of Sideshow that was actually done here at Microsoft. And the user says, notifications are useful because they prevent me from having to go to Outlook, in this case Outlook, as often. So it prevents that notion of having to visually sample a peripheral display. And that's what I think is a primary utility of having notifications. But at the same time, as one introduces more notifications into the interaction, it can cause more interruptions. Okay? And there's been a lot of work done by Mary, by myself, and many other people in the field of HCI and human factors that provides very substantial evidence that interrupting people's ongoing primary tasks can have a significant negative impact on task completion time, on error rates, and feelings of frustration, annoyance, and anxiety, or what's often referred to as negative affect. And so what we'd like to be able to do is somehow maintain the utility of the notifications, but at the same time mitigate those interruption costs. And McFarlane calls this one of the most challenging problems in HCI today. Okay? It just so happens he works on the problem too. But if you look back in, say, the past 2 or 3 years of the SIGCHI proceedings, you see very talented people addressing this problem. And the amount of people doing the work here continues to increase. And so I think this is a very challenging, difficult, and interesting computer science problem. Okay, so I believe very strongly that we need to start thinking about system architectures that allow us to maintain that balance of utility and cost. But at the same time, I've always felt very strongly that interruptions are really a problem of human architecture more than it is of system architecture. And so my work, I got very interested in trying to understand basic theories of cognitive psychology to try to leverage some basic principles that might allow us to understand how we could develop system architectures that were consistent with human architecture. And in doing that, I thought we could perhaps achieve that balance that we're looking for. So many years ago, there's a very influential article that is referenced a lot in the interruptions literature done by Maudet and Norman, who argued that the lower cost moments for interruption would occur at the moments of lower workload in your task sequence. And they further eloquently argued that those moments would occur at the breakpoints in either the task or the subtask sequence. And so if I slip up and say boundary, I use the term breakpoints. I'll try to use that consistently through the talk, but those two are synonymous for the purposes of my presentation. Okay, so what does this mean? I'll just take you through a very simple example. So you have Microsoft Word and a couple of comments that a person needs to address. You do a hierarchical decomposition of the task. So you need to do the revision. You're going to do the first comment, the second one. To do this one, you have to review it, make the edit, review it, and make the edit. And what their theoretical arguments say is that, well, if you interrupted a person between the subtask breakpoints, that it would have a reduced cost of interruption relative to during the execution of any one of those subtasks. Okay? We also talk a bit about granularity of breakpoints. So the granularity of this breakpoint is finer because I complete a smaller chunk of the overall task execution. And the granularity of this breakpoint is slightly larger because I complete a larger chunk of the overall task sequence. Okay? This fits very nicely with what Kahneman and Wickens have talked about in terms of resource theories of attention allocation. And so if you can interrupt a person at a moment of lower workload, then they have more attentional resources that can be allocated to the interrupting task, and they would require fewer resources to get back onto the primary task. They also have many, beyond the theoretical underpinning, breakpoints also have many practical advantages. One is that all goal-directed tasks, of which desktop computing tasks are instances of, have breakpoints. And second, if we can kind of develop this theory a little bit better, I'm confident that we can build systems and or statistical models that can detect breakpoints in users' task sequence. Okay? So they not only have some theoretical advantages, but they also have some practical advantages. Okay, so a lot of my work has really kind of picked up on that basic theoretical underpinning and tried to develop it quite a bit further. So we've made a number of contributions in this area. The first thing that I'll show you today is that deferring the notifications until breakpoints in a task sequence can, in fact, reduce the cost of interruptions in terms of resumption lag, feelings of frustration, as well as error rates. I'll also show that why that might actually be the case. We did some work with mental workload, and we're going to show that mental load does tend to exhibit transitory decreases as people move through breakpoints in a task sequence. And also we find that the different granularities of a task sequence matter. Okay, so different granularities have different costs in that hierarchical decomposition. And also, as I talk about that work with the physiological measures, we'll learn that we don't ever want to do that again. And I'm going to show you a method for actually predicting accurately the cost classes of breakpoints in that hierarchical decomposition, absent the use of any type of physiological measure. Most of our work then assumes that we have this nice decomposition like I showed you on the previous slide. I'm going to then talk about our latest work that shows how to detect breakpoints without knowledge of the task itself. Okay? And finally, I'm going to talk a bit about a system architecture that allows us to start thinking about how we can balance the utility and the cost for intelligent scheduling of notifications. Okay, so how does our work fit with the broader literature on this area? And there is a lot. And in the parlance of McFarlane's taxonomy, I think there's two strategies that are most relevant to what I'm talking about today. One is what's called a negotiated strategy. And negotiated strategies really are referring to peripheral displays. And this allows a person to choose when and how often they want to switch their attention from the primary task to the secondary display. These are very good for information updates that are relatively low frequency and of lower urgency. And once you have the opposite of updates that are higher urgency or higher frequency, these tend not to be as effective. Why? Because people start to visually sample, and all the studies show this, that users will start to sample and pull the secondary display, which in fact is distracting itself to the primary task. And so the tendency is, in these types of displays, is to render attentional cues, such as an audio alert or an animation or something like that, to grab the user's attention. So I think our work actually contributes to this area by helping them identify moments that it would be more appropriate to render those types of attentional cues. And second are the mediated strategies. This is where you try to have a third party, a system that tries to mediate the flow of notifications from applications to users. Eric, of course, has done some fantastic work in this area. James Fogarty from CMU has done some great work in this area as well. The way our work is different is that we're trying to show the value of using the structure of the task. Okay? And this would just have to be one part of a broader, more comprehensive system that takes into account many other cues. But what I want to show you today is that if you take into account the structure of a task, it can achieve a favorable reduction in cost of interruption. Okay, so what I'm going to do now is I'm going to move on to talking about our first study and the results. I have 6 years' worth of work that I want to talk about in 45 minutes. And so I'm going to focus on breadth over depth. I have references to the papers, and if people want more details about the methodology or further analysis of the data, I'm going to try to just give it to you in summary form as best as I can. This is also probably a good time if there's any questions about terminology or just basic things. Nothing, thought-provoking things, we'll probably wait till the end, but any questions? Okay. So the first thing I was interested in looking at is, do breakpoints matter? Nobody had really studied this systematically yet. So I was interested in the questions, do breakpoints matter? And I wanted to start with a very simple setup. And so the idea is I would have a user engage in 3 task trials. So a sequence of 3 tasks. I had 6 different categories of primary tasks, having a representative sample of interaction. I had image manipulation, registration, counting, adding, selection, and so on. I'd also have 2 different types then of secondary tasks. Okay, I had one that was an analytic task and one that was a reading comprehension task. All I would do is that for 2 of the 3 primary tasks, I would deliver those peripheral tasks either during or between the task sequences, okay? So at the course breakpoints. And that was the only manipulation. So one of the key things here was I kept the task load constant between the 2 different groups. I had 25 in the between group, 25 in the during group for a total of 50. And I simply changed the time at which I notified them, okay? Or I delivered the peripheral tasks. I had the 3 primary task trials and only 2 of the secondary tasks to control for what's referred to as an expectancy effect, where users try to come up with strategies to cope with an impending interruption. And so if you randomize it with 2 of the 3, then it's more difficult to do that. Okay, so we're clear on the experimental methodology? Okay, so let me just jump right into what we found with this. And this is just a subset of the results. And if you want more details, I'd ask that you just look at the article on this. Okay, so the first interesting result that we found is that when the peripheral tasks are delivered between the primary tasks, users experienced 47% less increase in anxiety. And so the way we did that is we measured it before and after the study, and I took the difference between the 2 measures. Okay, I used the state trait anxiety inventory form, has a scale of 0 to 80. And I did that between the 2 different groups. And for the group that got interrupted, they had a relative increase of about 12 points. And for the other group, it was about 6 points. Okay, so they actually the anxiety increased less for the group that had the peripheral task between the primary tasks. In terms of annoyance of receiving the peripheral tasks relative to each of the different categories of primary tasks, overall there's about 36% less annoyance that users reported. They had few errors overall, but there were 50% fewer errors in the between group than in the during group. When the peripheral tasks were delivered between the primary tasks, they had no negative impact on the task completion time. And so I had 1 control task in each set. And so comparing that control task to the performance of the other 2 that had the peripheral task after or during it, there was, in the between group, there's no negative impact on task completion time. Not surprising because they weren't really interrupted, right? It came in between. And in the other group, there's a 3 to 27% degradation on the interrupted tasks. Eric.
Are you done with the slide yet?
Please, go ahead. I'm not done with it yet, but please, go ahead.
No, I'm trying to be careful to get your break point. In less controlled studies, you might have a metatask in place that's very active and very important, which involves planning between phases of activity that are more explicit, like the ones you have here. Yep. Where in your controlled study, people are saying, resting for the next task. In reality, real world people are buzzing about their plan, and so that might lead to an artifact of the study.
Absolutely.
A real world interruption. It's very important.
Yeah, absolutely. I completely agree. And you just took the next words out of my mouth. That's exactly. So I wanted to just put these in perspective a bit. I mean, the first thing is, would you get the same type of effect in a more practical computing situation? Probably not, right? Because there's all other factors that aren't being considered here, exactly what you were saying. But I do think that if you did this over time, you'd start to yield these types of favorable reductions, okay?
Yeah, I just worry about that. Very hard to get at
Yes.
reflective planning
Yes.
cost.
Yeah, no, so I agree. And here's why I did the study the way I did it. If I couldn't show a favorable reduction with this set of tasks, there's no way I'm going to show it with what you're describing. And so I wanted to do the very simple case first to actually show there might possibly be a favorable reduction, and then start doing things that are more complex after that. Because like I said, if I couldn't show it here, there's no way I'm going to show it anywhere else. Okay. The other thing I would mention is that the differences between the timings, okay, between during versus between, were relatively short. It was on the order of a few dozens of seconds, and that was it. So it seems to suggest, though it's fairly controlled, and you have to take it with a bit of caution, that if you defer things to breakpoints, it can, in fact, have a positive benefit. Okay? So that leads into actually the next study. And this study had, the previous study had very well-defined breakpoints between the tasks, right? I mean, it was set up to have that. But when you have more complex sequences, then what do? How do you choose the right points? And what was concerning to me is that all of the empirical literature on interruption did either random moments or periodic moments. And I was very concerned about the repeatability of that type of work. And even if you found something interesting in terms of the results, how would somebody replicate that in other types of situations? So I was concerned about not having a basic theoretical construct that would allow people to choose moments for interruption in a repeatable fashion. And so that led us to start exploring a number of different theories about this. And the one that we came onto was referred to as, is called event perception theory. It builds on unit identification methodology. And Zacks, Jeffrey Zacks, did this several years ago. He did it while he was doing his PhD work at Stanford. And what this theory basically says is that even though I'm perceiving the incoming sensory stimuli, and it seems to me my experience is very continuous, in fact, it's being discretized into discrete chunks. Okay? And it gets driven by a two-level cognitive schema that divides this into what's called coarse units and fine units. And he did a whole bunch of studies that demonstrate that this is the case. And we wanted to pick up that methodology and apply it to interactive computing tasks to see if we could identify where the breakpoints were in tasks that were slightly more complex and see what kind of result we could get. And so let me take you through the methodology, and I'll talk about how we formed our hypotheses. Okay, so we did 3 tasks. We had a media summarization task, a web search task, and a document editing task. And we record ourselves doing the tasks. We take those videos and we showed it to 30 people. And the 30 people then annotate, well, we give them instructions. Every time that you see a transition between meaningful activities, write down a brief explanation of what that activity is. You have them do it twice. The first time, the instructions are the switches between the finest level units that are natural and meaningful, and we use the same terminology that Zacks used in his work. And the second time they do it, focus on the transitions between the coarsest units that are meaningful and natural. And what's somewhat shocking is that people pick the same points. Okay, so you merge all 30 together into this 2-level hierarchy, and you just create a frequency distribution of how often people mentioned each one with relative linguistic tolerances for that. And the hypothesis would then be is that the coarse breakpoints that are identified most often would be the best moment for interruption, and in between the fine units that people agreed least often would be the worst point for interruption. Okay? And so then what we do is we do another study. We have a different set of users. So we have our basic points that we can hypothesize that are better or worse, and we run a separate study with different users. They do the same tasks that the original set watched, and when they hit those points that we had predicted, we give them a little notification. They do the task, we dismiss it, and they get back on to their actual task. We pick the points simply by having a real VNC client interface so we can watch what they're doing. And the measures that we took were subjective workload through the NASA TLX, frustration, and I guess we had read a whole bunch of Clifford Nass's papers, so we included social attribution, which is respect for, from the interrupting task. And here's what we found. Best relative to worst, and there was no one task that was anomalous relative to the others. This was actually true across the tasks. It reduced the reported levels of frustration by 33%. It improved the social attribution by 30%. It reduced the sense of time pressure, which is one of, I think, 5 dimensions on the TLX. This is the only one that was significant, by 45%. Relative to random, we got a very similar outcome. So again, overall, I thought this was pretty good. We have to take it with a grain of salt because it's a controlled study. It's not necessarily a practical computing tasks. But what I thought was really exciting about this work is that we had found what we hoped would be, though we only had done one study with this, a theoretical construct that people could use to pick out the moments for interruption in a task sequence. And I thought that was really exciting for the work. Yet at the same time, I was very concerned about accepting Miata and Norman's original arguments that mental load is lower at the breakpoints between different chunks of a task than other points. Right? And what I was concerned about is that basically perpetuated itself through the community with no actual test. And I wanted to test whether or not that claim was actually true. Whether I could find a result, I wasn't overly concerned about, I guess, but I wanted to test it. Okay? And so the way I wanted to test it is to come up with a set of fairly controlled tasks, have our hierarchical task decompositions, and then I would monitor their mental workload through a physiological measure continuously, and go through a lot of work to then precisely align them down to the millisecond level. And I could then determine at every point in the task what the workload was at one point relative to a different part of the task. Okay, so we developed 3 different tasks for this study. We had a route planning task, we had a document editing task, and we had an email task. So for instance, on the route planning task, you would just copy information on distance and fare information from the map, put it into the tables, do it 1, 2, 3 times for each of the segments, add them up. Same thing for the second route, and then add up the distances and fares here, and select the shorter and the cheaper of the route. Standard document editing task, read 2 different comments and make modifications based on that. And then we did an email classification task, where based on the subject descriptor, you would classify this into one of the folders, go back up, get the next one, classify it, drop it in, get the next one, and so on. Okay. So we designed these to have a fairly representative set of the kind of the sub interactions. We needed a fairly prescribed sequence because all the users needed to do it in the exact same way, so that we could test their workload at the various moments. They needed to have fairly well-defined breakpoints. And we built hierarchical task decompositions using GOMS models. We spent a lot of time on the GOMS models to make sure they were really accurate. On average, they had about 4 levels, 80 nodes. The error rates are pretty small because we did put in a lot of effort to make sure that they were accurate. And there's no observable patterns to the errors themselves. For our measure of workload, we used Pupillary Response. We selected this because it's global, and so it gives you a sense of workload at a holistic level. It doesn't actually discriminate between verbal and visual processing. It's more in a holistic sense. Fairly low latency. It's about 250 to 500 milliseconds after the onset of a task. Your pupil will ever so slightly increase due to mental processing effort. It's very well studied. It actually goes back to the late 1800s, where people are looking at the size of a person's pupil to gauge interest in their stores. But it's been studied systematically since at least the 60s. Most papers show the correlation between workload and pupillary response. We didn't just jump into this. We actually did a lot of smaller scale studies up front. I worked with a number of cognitive psychologists at the Beckman Institute, and in particular George McConkie, who's one of the world's experts in eye tracking. And I actually have the cognitive psychology students, somehow I tricked them into running the study for me, which is good. In terms of characteristics, the average human pupil is about 5 millimeters. It'll range from 1.5 to 9, and it actually gets smaller the older you get, until it closes off for good. You have to be careful. I mean, it's not going to pop out of your head, right, if you induce mental processing effort. The largest increase I've ever seen is 40%. It's usually going to be around 10 or smaller. You have to do a lot of processing effort to extract out the workload data from the raw pupil data. You have to filter out eye blinks, which actually the eye tracker helps you. You have to adjust for that latency effect, and so you have to shift the pupil data over ever so slightly. And you have to calculate what's is called percent change to account for relative differences between users. So it's just the sample of data minus a baseline that you take at the beginning of this experiment using a blank task screen divided by the baseline. We used a head-mounted iLink 2, which is one of the best eye trackers available. It samples the pupil at 250 times a second to a resolution of about 100th of a millimeter accurate. Analyzing this type of data is just enormously difficult. It took us probably a year and a half to do the analysis of the data. In that time, we actually developed a new interactive visualization tool that can help reduce the effort. And we actually used the tool to do the analysis towards the latter part of the work. And I actually think talking about the tool helps understand what we did for the analysis. And so it just has an interactive overview plus detailed visualization, where my overview, what I have is a time-based visualization of the task model. And so the way that you compute the time for each of the different subtasks is you look at the video of on-screen interaction that's recorded by the eye tracker, and you look at the cursor cues, the gaze cues, and just the state of the task. You match that to your task model, and you pick out the timestamps that get overlaid, and that tells you precisely when each subtask starts and ends. Okay? Then you compute those times, you put them into an XML file. When we read it in, we simply show a visualization of the length of time for each one. So naturally, the root node expands for the entire duration of the task, and they get progressively smaller. For the continuous measure here, this is the actual workload data that you can see basically goes up and down throughout the task model. And then you have a magnification lens that allows you to zoom in on parts of the data and look at it in greater detail. So what we're interested in doing is really just exploring, say, what was the workload, say, during the adding tasks versus the other parts of the task? What was the workload at the more significant breakpoints than the other parts of the task? This is an example from the email classification task of the data. And let me just say that I made a lot of effort to compare this data to dozens of other papers on pupillary response. And the data is very similar to what other people have found. So I have a lot of confidence that our data was good. What you notice is that there's a lot of fluctuations in workload, which you might expect. And the thing to really notice about this is that this is the email classification task. So during the points where you have the stars, that's where the person is moving through the breakpoints. Okay, so I can probably do it better with the cursor. But every time they move through those points, what you see are these kind of transitory decreases as people move through that. So they're making some effortful processing to reason about which folder it should go into, and then there's a release, processing, release, processing, release. And that's pretty much what you see. It's not true for all of them, but it's true for most of them. And we found significant differences in a statistical sense between those. So across all three tasks, here's what we learned. One is that the workload does seem to fluctuate during the execution of a primary task. That gives you a sense that people are doing adaptive allocation of attentional resources as opposed to allocating all resources up front and then applying them throughout. This gives more evidence that says that the time at which you interrupt a person in a task matters because the workload is fluctuating. Second, we found that there are transient decreases at some breakpoints in a task, and it typically was the ones that were larger cognitive chunks. So at the breakpoints, what I call higher in the task model, so like level 1 and level 2, you would find those small decreases as a person moved through that part of the task. After that, you really don't find anything. There's too much carryover, they're too short, it's too rapid, and you don't really find much. But if you want to know exactly the rank order, you pretty much have to align the measure of workload with the task model itself. Otherwise, you can simply use some basic heuristics about, well, just pick out the things that you think are the coarser grained breakpoints in the task. Very consistent with what we found in our prior work, okay, and very consistent with what the theoretical arguments were here. So is this black magic? I don't think so. I mean, I think all this really says is that there are points in a task where people take short mental exhales. And when they do that, there's a temporary reduction in the mental load that's detectable through changes in pupillary response. Okay? Eric?
We talk about load as a almost like a homogeneous substance, and we know that there are different kinds of loads and different kinds of mental activities.
Yeah.
For literature, I guess the pupillary response is usually a general measure, but what's your sense for different kinds of things going on and influence that might go beyond our ability to detect with pupillary response relevant to the interruption problem?
So absolutely. I think, so there's a lot of work on what's called multiple resource theory, is that if you have different pools of resources, basically. Pupillary response does not allow you to discriminate the usage of the different pools, but something like EEG would allow you to do that. And that can be useful, because if you know people are using the verbal part of the brain, then you might want to have something that's more of a visual modality, and vice versa. Okay, so yeah, you can do that. We actually just tried a study that looked at cross-modality of interruptions. We're still trying to sift through the data, but hopefully we'll have something in a few months. But we did look at that, actually, for exactly that reason. Okay, so the next thing we wanted to do is actually evaluate whether or not the predictions that we could make based on this would actually have a reduction in cost. And so what we would try to do is take the boundaries based on the workload aligned models and use them to predict where we think the better and the worst boundaries were, and simply which ones had the higher and the lower workload. Okay? And so we did this across the tasks. We had the best, we had the worst, and we had the random. Our hypotheses would be that the best was better than random, best would be better than worst. Didn't necessarily care between worst and random. Our measures were resumption lag, annoyance for effective state, and social attribution. Okay? And the key here is that the way we picked the points was simply looking at those workload-aligned models. Okay? Finding the points that had the lower absolute workload values and the points that had the higher absolute workload values for the boundaries themselves. And here's what we found. Best relative to worst, and again, there was no one task that was weird relative to the others. This was true across the tasks. We found 70% less resumption lag. We found 18% less annoyance, 37% more respectful. And best relative to random, we found similar results. That some of them were only marginally significant.
I was wondering if you could tell me why do you not care about worst relative to random? You said you didn't really care about that, but
So why don't I care about worst relative to random? I know I have an answer for this, and we thought certainly very hard about worst relative to random. Well, I guess one could look at that, Ed, and I'm just thinking about. We were really interested in the breakpoints. Okay, so we're very interested in the breakpoints, and so I wasn't, I guess, as concerned about worst relative to random, simply because we would never try to interrupt somebody during a non-breakpoint area, and so the study was mostly focused on looking at the breakpoints and seeing if there's a difference between the different granularities of the breakpoints, and because of that, I wasn't as concerned about the random points because I would never build a system that would do that anyway if I detect the breakpoints. Now, I have the data. So if we wanted to, we could go back and look at it and make the comparison.
It would be really interesting, especially from a theoretical point of view, to see for your model. I mean, if it really is worse than random.
Yeah, you're probably right.
Then you're gonna. That's a really nice, finding.
All right, so maybe the two. Okay, thank you. Okay. Again, though, the results seem to be consistent with all the things that we've been saying up until this point. Okay, now. We don't want to have to use physiological measures to keep Microsoft Word from interrupting us. Okay, it's far too much work. And so the next idea was that if we could leverage the characteristics of the structural elements of a task decomposition, essentially to approximate workload and make accurate predictions of the cost of interruption. And for this study, we're going to use an objective empirical cost of interruption called resumption lag, which is simply how long it takes a person to finish the interrupting task and get back onto the primary task in terms of their first directed action towards, I think I want to call it, the goal of the primary task. Okay, so just resumption lag. We used two tasks that were similar to what we did before, route planning and the document editing, and we added in a video editing task. We try to keep these prescribed yet still allow for some variability. We build the GOMS models, the hierarchical task decompositions. We don't go down to the very basic operators to allow for some variability in the task sequence. I think we went to about 3 to 5 levels deep. And what we would do is we had I believe 12 users come in, and they would do 5 trials of each of the tasks, and we'd interrupt them at a sample of the 2 boundaries. Okay, or just a random sample of 2 boundaries, 5 tasks. We got about 330 data points for resumption lag. And again, comparing this to other values that people report in the literature, it's very consistent with the data that we collected. And what we're interested in is in looking at the different properties of this decomposition to see whether or not we could predict these values. So we looked at things like what was the overall percent of the task complete, what was the overall percent of the parent task that you completed, where there's a noticeable visual resumption queue available, what was the level in the task model, how much mental carryover was there. And some of this we had to do some subjective coding, but we used standard techniques to do this. What we found is actually quite intriguing. We found that the depth or the level in the task model, so the granularity of the breakpoint was predictive. We found that the mental carryover and difficulty of next subtasks, both using standard techniques for how you actually encode those values, but it is somewhat subjective, so you have to take that a little bit with a grain of salt there. But we found that those three characteristics were most predictive of the resumption lag. And here's why I find that fascinating. Out of all the things we studied, this is current and prospective allocation of resources, workload. I thought that was really amazing. Now, the correlation coefficient was fairly modest, okay? Those three characteristics explain 26% of the data. So what we wanted to do was trade off precision for accuracy. So I would group these things into larger cost classes so I could predict the class as opposed to the actual numeric value. Okay, so I could boost up the accuracy at the loss of some precision. So we do the standard k-means cluster analysis technique. We play with a number of different values. And what we came up with is that 3 different cost classes were appropriate. Okay, and I just called them cost of low, medium, and high. And I thought it was very interesting that was consistent with what James Fogarty reported in his work on task engagement in 2005 at Chi. And what this says is that absent some kind of real-time measure of workload or other information, the best that we're going to be able to do with interruption reasoning systems is to discriminate between 3 different cost classes. Okay, so we did some just standard machine learning, used a Weka toolkit, threw in the numbers, and it spit back out a neural network. What we do then is for each of the hierarchical task decompositions, we compute the granularity of the level, the carryover, and the difficulty using the techniques that we developed, and then we put in the the actual cost classes based on the numeric values. We just learn the mapping between them. And what we got in terms of the training results, or the results on the original training set of tasks, is we got an overall 63% accuracy of predicting the cost classes. That is better than random with 33%, and it's better than picking the one that occurs most often, which in this case would be the medium. Looking at the confusion matrix, the diagonals represent where we got it right, and the other areas represent where we got it wrong. The one I was actually most concerned about would be the most egregious type of error. And all right, who's paying attention? Which one is the most egregious type of error? Which one is the most egregious type of error? Nobody's paying attention. I have to put the question in to make you think. The most egregious type of error would be what? When we predict low, but it's actually high. Right? And that was only 5%, so that's pretty good. We also wanted to test whether or not this would work for a different set of tasks. Okay, so we basically went through the same process. We did the hierarchical task decompositions. We did a collage generation task and an Adobe Forms design task. Same process before. A different set of users came in. We computed all the predictions based on our model, and we would interrupt them at a random sample of the different breakpoints in the decomposition. What we found, we had a total set of samples of 134 resumption lag values. We got a total of 53% accuracy. Again, that's better than random, and it's better than always picking the one that occurred most often. Same type of confusion matrix. This time we got slightly lower results, but we had the overall same qualitative pattern. Okay, the one that's most egregious here did increase a bit. So the question is, are these results any good? Okay, let's see. So what I did next, and I think this was really the punchline of the work, is we went through and we clustered the values based on their predicted cost of interruption, not the actual. Okay, we used the predicted cost of interruption, not the actual. Here's why we did that: because it includes the errors. Right? It includes the errors that our system would make, and we wanted to see if it still would have a positive benefit. And what we found is that in the actual resumption lag values, the high cost had an average resumption lag of 2.6 seconds. These are in milliseconds. This is 1.3, and this is 0.87. Okay? All the pairwise combinations were significant between them. And so if a system would withhold the notification from the breakpoint predicted as a high cost to the breakpoint predicted at a low cost, you would save the user about 1.4 seconds in resumption lag. That's great, actually, because if you extrapolate that over all tasks, all notifications, and all users, it could actually be a fairly substantial benefit. And what I think is good about this is really one of the first studies that actually shows that a certain intervention can have a favorable reduction in cost of interruption. Okay? But it also tells us that we have to be able to discriminate between the different granularities of the breakpoints in a task. So now we got to a point where we could essentially, if you give me a task model, I have now this neural network that I can plug in the numbers and predict with reasonable accuracy what the cost of interruption would be at the different breakpoints in that. And what we wanted to do now is start thinking about, well, how would we operationalize that in a system? And what would be some of the challenges that we would have to overcome to do that? And so the basic idea was to, I'll just go through the architecture of the system. That'll be easiest. We wanted to first provide people with a language that would allow them to easily specify the task models that we saw earlier. Okay, they're not GOMS models. They're more abstract than that, and you can specify them any level of detail that you want. Okay, so you just have those types of models that I've showed all through the talk, specified in some type of description language. We have some instrumentation in the applications that are just sending us the application level events. It gets sent down to our event handler, and then you have a task monitor that simply reads in the task descriptions. It looks at the incoming events and just tries to match the two. Okay, following the user's progress through the structure of the task. That's what we're trying to do. What I think is valuable about trying to do that is it automates a process that we've already shown works. When an application then wants to gain the user's attention, it would send a request and a time frame to our system. And what we try to do in that time frame would be to find the lowest cost moment of interruption. Okay? How do we compute time frame? I don't know. But I would imagine that we have to map the urgency and the relevance onto that. And this is certainly an area that people have to focus on in the future, is how do you compute utility of a notification relative to your task? And I'm hoping Eric will give us the answer about how to do that soon. Okay, so that's the basic overview of the system that we're trying to construct. As a first step towards developing that system, what we did is we created a framework for specifying and monitoring user tasks that we just actually recently published in the Journal of Computers and Human Behavior. So I'm going to just give you a brief overview. If you want the details, I'll point you to that article. In terms of describing the tasks, it draws upon XML, and we used regular expressions. It has three key elements to it. You can identify the events. And these would be the applicational events. I would describe this as if you were to narrate to another person, the steps that a person goes through, those equate to what we have in terms of the task description. You can use the natural part of XML to just express a hierarchy. And so you can have any level of detail that you want. And you can use the regular expressions to express variability in a person's task sequence. And in fact, that was probably the biggest challenge of building the language, is how do you allow for variability in the task sequence. So this is kind of a representative example of somebody doing a calendar update in Outlook. This is the names of the events correspond with what one would sort of get out of the scripting engine with Outlook. But the basic idea is that you can specify the steps that one might go through and specify some of the variability so you can follow people, hopefully regardless of how they do the task. Okay, so you might say, like, well, scheduling a sequence of appointments, you have to do one or more of adding the appointments. You have to do the following in order. You have to open the appointment item. And then you don't have to do either. And if you do, they can occur in any order of making a change or writing to it. You can close it, and then you can switch focus to something else. And it can do those sub-steps any number of times. Okay, this is about the granularity at which you'd have to do the specification. And what I want to make clear is these are not GOMS models. We're not trying to go down to the elementary perceptual, motor, and cognitive sub-steps. You can do this at any level of detail that you want. So if you simply wanted to catch application switches, you could do that with this as well. If you wanted to go to every precise sub-step, you could do that as well, based on what you have for the instrumentation of the application. Okay? Then what you can do is you have an attribute for the cost. Okay? And hopefully you could use in our previous models to predict what the cost ought to be at each step, then insert that in. And then the reasoning system could use that to make more effective decisions about when to trigger the notifications or to let them through. Okay, in terms of the task monitor, what this does, it reads in the task descriptions, it looks at the incoming event stream, and it tries to match the two. We use a relatively simple algorithm. I just call it the position placeholder algorithm. Once you have an event that comes in, you look to see if it matches any of the first events in the task descriptions. If it does, you instantiate it, and you put a position placeholder. And the basic challenge here is simply understanding when you advance the pointer, when you keep it the same, and when you basically destroy the task description. Okay? We built on an algorithm that Chikes and others did for intelligent tutoring back in '98, but we extended that to support multiple active tasks and multiple instances of the same task. And that's the basic contribution of the task monitor itself. You do have some ambiguous situations. So what happens if there's multiple task descriptions that match the same event? We just pick one very easy way to do it, just first come, first served. Okay? But certainly there's probably more advanced mechanisms that a person could use. Okay, questions on that? Robert?
So I'm trying to understand how this would be realistically deployed, because certainly, the cost of entering this task, it takes many 1.4 second savings to add up to one session of writing an XML file, right?
Right.
So is the thought that so if we wanted to get Word to do this, is it that the Word team would come up with a library of 50 common tasks or something, and that would be kind of encapsulated with Word, and in the background it would do this?
Well, thanks for asking that question. I think that's a very good point. Who benefits most? Who has to do the work? Certainly, you would probably not want to build these types of descriptions for every task and every application. I would focus on high-frequency or critical tasks, and you don't have to go. I mean, we actually did some user studies on this, and it's actually reported in the journal article. But on average, you can build reasonable descriptions in just 30 lines of XML code. So they don't have to be really fancy and complex. They can be relatively simple. If you focus on the higher frequency tasks for the more commonly used applications, I think that you could have a pretty good benefit with actually relatively little cost. You only have to build the descriptions one time, then everybody gets to reuse them. And so we would spur the community to do this because people would see the value, and then they would just want to build the descriptions.
I'm just kind of curious, how long does it really take? Just pick a task and just use. How long does it
Okay,
take?
so we studied exactly that question. And we picked out a web hosting task, a calendaring task, and I think it was an email classification task. And we recorded people doing it. We had their event streams, and we had, I think, 8 people come in and actually use our language to describe those tasks. And that's where I came up with the number of 30. It doesn't take them much longer than it does to watch the original video of what the person did so that you knew what the steps were to build the descriptions. So I don't really think it takes a lot of work, but you have to know what the event streams are. And of course, you have to get them from multiple people, and you have to understand where the different interleavings are. So we did study that a little bit. But I certainly concur with both of your points that, this might be, even though the cost might be minimal, that in itself might still be too much. And that takes me to the last part of my work. Go ahead, Robert.
I mean, it would also be interesting once these things exist to go back and study them and see whether a much more naive approach might not work. For example, maybe it's the case that every time you hit file new, that's a great time to interrupt.
Just exactly what we decided based on our research.
Right, exactly. Like maybe just certain operations are indicative of being in between big task switches.
Thank you. You just gave me the segue to the last part of my work, and we had the exact same thoughts. So here's the question that I posed: can we identify breakpoints without knowing the structure of the task? So without any knowledge of the task, can we identify the breakpoints? So what we did is we went back to that work that we did on event perception theory, which builds on what's called unit identification methodology. And basically what you do, and this is what I find most fascinating about the work, but if you have several people watch the same activity, people tend to agree on where the breakpoints are, which tells you that we have basically shared schemas that drive perception of action. That's really cool. Because if we can show that for interactive tasks and people agree on where the points are, then what we can do is we can pick up on the interaction cues that are ongoing, that people are perceiving, and use them to map to different types of breakpoints. Okay? So that's what we did in this latest part of the work. We studied 3 different kinds of tasks. We did programming tasks, graphic design, or I'll call image manipulation tasks, and document editing tasks. And we collected data actually from the field. So we had professional workers in each of these 3 areas use some recording software that we developed and log their own tasks for about an hour. And the instructions were as follows. The next time that you are primarily focused on the assigned task category, start the logging software, let it run for about an hour to an hour and a half, and then we'll come collect it. While you do that, though, just do everything else as you normally would. Okay, just basically forget about the logging software and just do everything else that you normally would. We had a very fundamental question then, is how many breakpoints should we look for? So the event perception theory argues for 2, but all the empirical work on interruption shows 3 cost classes. So we actually went with 3. And for the lack of better terminology, coarse, medium, and fine. Okay, so we're interested to know how often they occur, what are the characteristics that are going on that cause people to identify each one of them, and could we build models that would then map to them? So we had 24 observers, 8 in each category of task come in and watch the video sequences, and they would then hit a button here that says basically fine, medium, or coarse, and enter in a linguistic explanation of why they thought that was a breakpoint, because we wanted to kind of elicit out for them what they were looking at would help guide the types of features that we might use later in a model. Now, we used observers and not the users themselves. And that was very important, because if we had used the users themselves, I was very concerned that they would be using their own understanding of the task itself to identify the breakpoints. A model would not have access to that same information. And so we used observers because it would match what a model would be, an external observer of the interaction sequence. Okay, so we collect all this data, and here's what we find in terms of the characterization of the breakpoints. What you might suspect is that we had about over 3,000 breakpoints that were detected in that sample of data. 756 for coarse, 1050 for medium, and 1268 for fine. So it has this kind of nice hierarchical structure, kind of arguing that not only do people multitask, but they multitask at different levels of detail. Now, this is not true for all the tasks. So if you look at P2, you actually have the inverse effect. Okay? So this you had the most coarse and the fewest fine. Why? Well, because people are basically crazy when they're actually interacting with the system, right? And all this really says is that some people were doing less of the kind of detailed editing, and they're just switching all over of different applications. Okay? And in talking with Mary and Eric, that seems to be fairly common. And so for some, you had kind of the opposite effect, but the majority of the case here, or the summary case, was that the fewest coarse and the most fine. Okay, so what did people say about the breakpoints? They said that the coarse breakpoints were switches to activities that were unrelated to the primary task. And there's some human judgment then about the content of the different applications. Medium was a switch in the source object, so a different image, a different document, a different source file. And it could be a switch to an activity judged to be relevant or related to the primary task. And the fine was switches between actions on the content. Now, this didn't count for all of them, but it seemed to be the consensus that emerged from the explanations.
Just a quick clarification. Your observers, were they experts in the tasks they were watching, or were they naive about the tasks they were watching?
Oh, great question. And if you look back in the work by Newtson and Zacks, what they argue is that it doesn't matter in terms of familiarity of the task. And so we didn't actually judge for that. I know it sounds crazy, but they actually studied that in great detail and found that there was basically no difference between people that had familiarity and people that didn't. And the argument there is that there's something more kind of fundamental up here that goes on in terms of the schemas that we have that drives perception of action. In terms of the time between the breakpoints, they're on the order of a few minutes. Okay, so multitasking, of course, is very common, but again, it happens at multiple levels of detail. And so when a person hits a fine breakpoint, we're interested to know, say, how long would it be until the next one? And so the distance to the next one would be just under 2 minutes. The distance to the next medium would be just about 3 minutes. And the distance to the next course would be about 7 minutes. Okay, so this gives us a sense of if we were to try to do this deferral policy, of defer until the next breakpoint, what would we realistically expect to happen? AJ? I'm sorry, standard deviation.
Oh,
so this is average and standard deviation, and this are all in seconds. Okay.
So there's some big ones.
There are some bigger ones, yeah. So I think this is the biggest one. This is about 7 minutes, and that is from from a fine breakpoint on average to the next coarse breakpoint, collapsed across the different types of tasks. Okay, so now we're looking at could we build models that would actually predict these? And the first question is, well, how should we do the models? We weren't exactly sure until we looked at the characterization of the breakpoints. And in talking with people who know a lot more about machine learning than I do, we came to the conclusion that we should use a coarse, what I would call a model for the coarse breakpoints, since that was across the different tasks, and then a model for each of the specific applications that would do both medium and fine. So we had a total of 4 models. Okay? 1 for the coarse breakpoints, and then 1 per application for medium and fine. We looked at a whole range of different candidate features. Okay, these came from the linguistic explanations, what people have reported in prior work, and kind of our own understanding of what was in the tasks. Came from 4 sources: the window switching behaviors, how many applications were started, exited, minimized, maximized, and so on. Actions on the content. So we looked at things like, did you just finish a sentence? Did you just start a new paragraph? Did you finish a line of code? Did you just do a blur operation in the image manipulation? Keyboard entry and cursor movements. Okay? The only thing that we did funky with the candidate features was that thing about the course breakpoints. Because remember I said that the users reported that it was switches between activities that were unrelated to the primary task? That's very difficult to assume that we're going to be able to do in a model. So we didn't actually try to do that. What we did is we created higher level categories such as entertainment applications, online news, online shopping, and then each of the different task categories, and simply counted the switches between those. Okay? Because that would be kind of the low-hanging fruit that we could easily detect in a system. We did a whole bunch of work on filtering the breakpoints to remove the noise from the data. And what I found most fascinating about that filtering process is they line up amazingly well. Okay? And then we learned neural nets that would map the characteristics that we had, the candidate characteristics that we had to each of the different types of breakpoints. And when you do that, you also have to include in a number of different cases for when there was no breakpoint. We just did that as a random sample within each of the task categories. Here's what we found. For the observers, we found 80% detection accuracy for the course, 76% for image manipulation, 69% for document editing, and 76% for programming. And that was collapsed across different types of breakpoints, but there was no one anomaly. Okay, we had very similar results for each different type of breakpoint. If you want to talk to me after, I have all the confusion matrices for each of those tasks. But since I had 4, I didn't think I was going to actually be able to talk through all of them. So pretty good. Okay. Now the other thing that we did is we had each of the original users' data that we collected come back in and annotate their own breakpoint. And then we compared our generalized models to those annotations. And again, we got slightly less results, which you might suspect, but overall the qualitative pattern was pretty good. So we got 77% of the course, 68 and 86 for image manipulation. And again, I have 2 here because we had 2 users in each category. 56 and 73 for document editing, and 50 and only 14 for programming. Why do we get only 14 for programming on the second user? I don't know, other than say that the models just didn't work well for that particular person. To increase accuracy of these types of models, you have to find more predictive features, or you have to train it on a user-specific basis. But overall, I thought we did reasonably well, and I'm fairly convinced that this could be implemented in actual systems, and I do believe that the breakpoints occur often enough and that we can detect them well enough that you can do deferred breakpoint policies in practice.
Please correct me if I'm wrong. So the way you are training your models is against the labels that you think are the breakpoints, right? That's determined by your policy, right? And then you train those models, and then you ask the user to sort of specify what are the breakpoints according to their criteria.
Well, we already have the data from the observers. So they've already told us where the breakpoints are. We take 10-second bins around that point, and we compute the values for each of the candidate features. And that gives us the rules that or the training cases, okay? We throw into that set a random sample of places where there were no breakpoints and what the values of the features at those points were. That way we can discriminate between coarse and not a breakpoint, and we can discriminate then between medium and fine and not a breakpoint. Okay, and then we did the same thing for the user's points and reapplied the models and got these results. I'm happy to follow up with you about that. Okay, so that basically concludes my talk, but let me just end with some future challenges here. One of the challenges that I see is that we have to understand how to dynamically compute the utility of notifications. Nobody's, I don't think, has really taken a hard look at that, but we need to. We need, of course, to deploy and start studying these things in practice for working systems. We also need to start looking at how you design minimally intrusive notifications. So as Mary said, even if you get it wrong, it would still have a minimized impact, and I totally believe in that. And also, I'm very interested in how do we apply these types of principles to other domains that perhaps are more compelling than just office environments. Not that I think there's anything wrong with doing office environments, but I'm very interested in applying principles of attention, say, in intelligent driver support systems, which is a project that we're just starting at Illinois. I would like to just thank all of my very hardworking students, and I'll wrap up there. So thank you.